Welcome to Virtual Level Chemistry, Covalent Compounds. This is Unit 4, Day 3. We're going to start today with a warm-up. Alright, first warm-up question. Which pair of atoms will transfer electrons when a bond is formed between them? When we're looking at our choices, we can see that we had choice A says C and O. So for C and O, neither of those are going to transfer because those are both nonmetals. That's definitely covalent. So really what this question is asking you to do is to understand what the word transfer is meaning. So if there's a transfer of electrons, you know that's an ionic bond. So we're looking for an ionic bond. This is a covalent bond because these are both nonmetals. Alright, calcium is a metal. Sulfur is a nonmetal. That's looking good. P and Br, those are both nonmetals. So that one's out. Then we've got bromine and chlorine. Both of those are nonmetals as well. So transfer of electrons is something we only see with an ionic bond. The next one says, name I5Cl. So first thing you want to think of is be looking at that first one. Okay, this is iodine. So just by knowing that it's iodine, I should be able to figure out that, hey, I'm not dealing with an ionic bond. This is a covalent, bond. So we need to use our prefixes. Always name ionic bonds with the prefix. So then you have to next remember what all those prefixes are. So mono is for 1, di is 2, tri is 3, tetra is 4, and it's penta for 5. So penta is going to be my prefix here. And then for chlorine, we have to remember that there's an understood 1 if there's no subscript. It's not nothing, it's an understood 1. So that one I'm going to be using mono. That will give you my answer of pentaiodine monochloride. Alright, the next one says, write the formula for selenium diiodide. So our formulas for covalent compounds are so easy. There's no crisscrossing, none of that. So what you see is what you get. So selenium, Se. There's an understood 1 because we don't write mono in the front. Diiodide. So that means this is going to be a prefix of 2 on the iodine. And that's it. Okay, next one. Formula for tricarbon octahydride. Tricarbon, so C with the 3, octahydride. Octa means 8, so H8. Which is a covalent molecule. So this is the opposite of the first one. So the opposite was saying transfer, so I was looking for an ionic one. So for this one, I'm looking for a covalent molecule, which means I'm only looking for nonmetals. So if you see a metal, you need to cross that out. Au, that's gold, that's a metal. P and O3, those are both nonmetals. That's probably a good answer, but we'll check on the other choices. K is a metal. That's potassium. And Na is sodium, and that is also a metal. So, not a good choice. Alright, good job. Okay, a quick reminder, because this deadline is coming up soon. This 9 weeks is going to be over before we know it. So if you are not happy with your Unit 3 exam score, please make sure you make arrangements with your teacher, whether it's me, if you're a virtual learner, you're with Ms. Safford, or your teacher if you're remote at the moment but plan on going back. You need to retake that exam. All my students, you have access to an ionic remediation assignment. Before you have permission to get a retake, you need to make sure that that assignment is completed. It's in Canvas. It is called Ionic Remediation Assignment. Okay, so you need to do that. That's the Ionic Remediation Assignment and any missing work. And after that, you're going to be able to do a retake. All right, so we're going to keep it up. Today we are going to be talking about something called Vesper and molar masses. One of the key concepts, and this is not in your notes, but I really think that if you could just write this down somewhere, it's going to help you out a lot. I try and give you the most important couple topics. Linear shapes are going to have 2 or 3 bonds. Trigonal planar shapes are going to have 4 bonds. 4 bonds. And tetrahedral are going to have 5+ bonds. So keep those in mind, and we'll get into what this means in just a few minutes. Okay, the first part is a little bit of a review, so if you didn't understand this before, today is a great day to understand this. Lewis dot structures of elements. What does this all mean? It means the dots are really only representing valence electrons, okay? Valence electrons only. So if I see a Lewis dot structure right here for lithium, that means it only has 1 valence electron. Notice here are noble gases. This is neon. They all have their full valence electron shells. So these are only the valence electrons. Okay? That is review, but this will help you understand their shapes. So again, this comes from the number up on top. So nitrogen, for example, is in group 5A. So there are 1, 2, 3, 4, 5 valence electrons. Anytime you see a hole, right? So like, for example, the fluorines, they have a hole right here because they're missing one of those electrons. This makes the element very uncomfortable. It does not want to have an incomplete octet. So it's going to want to bond so it can complete its octet. So when we're talking about molecular models, these help us demonstrate the 3D image of a compound. Even though the atom is too small to see, we can predict its molecular geometry. Okay, we're going to see some examples. I'm also going to put a link in today's Nearpod for the PhET Interactive Lab to give you a chance to play with the interactive shapes as well. Okay, so when we have a covalent bond, you can either have a single bond where 2 electrons are shared, because remember, notice shared is in common with all of these. Okay, all of them are sharing because this is a covalent bond. Sharing is caring when you're covalent. Sharing is caring. Okay, so you can either have a single bond when 2 electrons are shared, like this right here. So these hydrogens, each of them have 1 little electron, 1 little electron. They can share it, making this. Okay, or what can happen is, see these oxygens, they both have these little single electrons. I'm going to make it a little thinner so we can see that. There's 1, and there's 2. Now they've both completed their octet. You see that? When they share. Or sometimes, in other cases with nitrogen, see there's holes there? That means there's 3 open spots on the nitrogen. So that nitrogen can actually form a triple bond, so none of those electrons are alone anymore. So basically the electrons that are by themselves will bond together, and that way there aren't any more lone pairs. And then one more. So they're not stealing them like in the ionic bonds. They're transferring. They're sharing. They're not transferring. They're sharing. So they don't get the electron all to themselves, but they're just content enough to share. So anytime that there is an unpaired electron, what they're going to try and do, if they can't find an ionic bond, they'll try and form a covalent bond so they can at least share. Okay? Now, for the types of covalent bonds that can form, you can either have polar bonds, which I think of the word polar, I think about like a polar bear, right? A polar bear may share with you, but it's probably not going to be equal. Like, right? So polar bears, they eat fish. They might get like 5 different fish, and they maybe will share half of it with you. It's an unequal sharing. In a polar bond, there's an unequal sharing of electrons. That's because one electron is stronger than another one. So think again about a polar bear. They're a lot stronger than you. They're going to maybe, if they share a little bit, you better believe they're going to take more because they're bigger and stronger. So they'll unequally share. And we're going to contrast that to nonpolar, which have equal sharing. Hold on. I'll pause it. Sorry about that. All right, so we just had a little announcement. So now we're going to talk about our nonpolar. So that is equal sharing of electrons. So this would be more like you and your best friend, right? You're nonpolar. None of you think that you're better than the other. You're going to equally share. If you're hanging out with your best friend, hopefully, and you go get ice cream, if it's not COVID time, right? You're going to share equally. Everybody gets the same amount. Okay? So those are our two differences. Polar bonding is unequal sharing because the polar bear is bigger and stronger than you, and it's not going to share with you equally, versus nonpolar, which is equal sharing. And here's a picture showing you like a good representation of an unequal share, right? Like these ones are way stronger. They're not going to share. All right. So first we're going to be looking at our single bonds. Here we have fluorine, bromine, and iodine. They all have the same structure. Notice all of them have 7 valence electrons, and they all need to have 1. If they have a single bond, they'll share. In the same way, fluorine, bromine, iodine, all because they all need 1 more valence electron, so they can pair together. And fluorine will look the exact same way, because fluorine also has 7 valence electrons. So here's a fluorine. So a fluorine will look very similar to chlorine. So I didn't draw those to scale, but we can see a single bond. So any halogen and also hydrogen will bond in the single bond way, because hydrogen only has 1 electron anyway. It would rather have 2 so it can look like helium. So hydrogen and halogens will form single bonds. Hydrogen and halogens. I would write that down. Hydrogen and halogens. These are the ones that are typically making these single bonds. Hydrogen and halogens. Double bonds are a little bit different. Double bonds are most often found with things in group 16. So nonmetals in group 16/6A. The ones with 6 valence electrons quite often form double bonds. Now let's think about why. So an oxygen molecule by itself has 6 valence electrons. So 1, 2, 3, 4, 5, and we'll just put the other one over here, 6. So remember I said anytime you have empty spots, it makes the atom uncomfortable. It would rather not have an empty spot here. There should be another electron, and also here, right? So they want to fill them up. They can do that by sharing with another oxygen. So when they share, the lines are just represented as the sharing. Okay, so it's going to find another oxygen, and it's going to be like, oh, I also need an electron right there. Why don't we just share? And then it's like we both have our octets full. So when you see that line, that represents a pair of electrons. And so now it's like they both have their octets full because they're able to share. And remember, they want to get to 8. So if we're counting, we can count them, right? I'm going to count the electrons, and I want each one to have 8. 1, 2, 3, 4. And remember, you can count these as each line represents 2 electrons. So I've gotten up to 4, 6, 8. Great, so this one's all full. And again, I'll count again. 1, 2, 3, 4, 6, and 8. Because each line in a bond represents 2 electrons. Same thing with our triple bonds. Nitrogen starts off and it's like, okay, I've got these 3 electrons that are unpaired, meaning these 3 electrons are looking to form a bond. So there we go. If they bond, now there are no unpaired electrons. That's a triple bond. So polarity. In covalent bonds, they don't have full charges like they did in ionic bonds. So remember those ionic bonds, they had that full +1, +2, +3 charges. Not the same in covalent bonds. But they do form partial charges, which actually end up being really important. Whether or not a molecule is polar or not will greatly affect how it interacts with other molecules, and we're going to learn more about this later. So this section is not in your notes, but I don't want you to worry about that too much. One thing I do want to point out, and that I do want you to know, is that water is a polar molecule. Okay, water is a polar molecule, and we're going to talk about that more later, but keep that in mind. There are 3 shapes that you need to know in level. Honors has a few more, but for level you need to know linear, trigonal planar, and tetrahedral shapes. And I will put links in the Nearpod for you to interact with these. Okay, so for a linear shape, that's our first shape, you want to think 2 or 3 bonded atoms, 2 or 3. So both of these are, this is the linear one, and this is also linear. They look like a line. A linear shape will look like a line. Okay, some examples are CO2 or H2. Okay, that is a linear shape. For its Lewis dot structure, I will do H. We'll do H2. So we got H. There's one H. There's another H. And look, they can make that nice little linear bond. Okay, and for CO2, same thing. I'll draw another Lewis dot structure. C, O. Actually, I'm going to erase this in because I'm going to run out of room. So I'm going to start that one again. Okay. Okay, so Some of y'all are going to be wondering, how do you know if there's more than two, which one to put in the middle? Usually it's going to be like the dissimilar one. So the C, for example, is, there's only one C, but there's two O's. So I'm going to draw the O's. And then I'm going to start filling in those valence electrons. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 1, 2, 3, 4, 5, and 6. So any time we're going to see, in this case, there's going to be some double bonds. That's also a linear shape, though. See how it's flat like a line? So that's linear. For trigonal planar, you're going to have 4 bonded atoms, so count the circles. So for linear, it was, you're going to be, if you were counting the circles, you're either going to see 1, 2, or 3. 2 or 3. For trigonal planar, it's going to be 4. So 4 circles, 1, 2, 3, 4. They have no lone electrons, and they're very symmetrical. And we were talking about before how boron is kind of a weirdo. Boron doesn't like to have a full octet of 8 because boron is strange. So it's very often found in a trigonal planar molecule. Okay? Trigonal planar. These will usually have boron in the middle. So this red one will usually be boron. They look like triangles, hence the word trigonal planar. The next shape you need to know and level is a tetrahedral. These will have 5 bonded atoms and no lone electrons. So count your circles. 1, 2, 3, 4, 5. These usually have carbon or silicon in the center. All right, so now we're going to change gears a little bit and talk about molar mass. So if you don't have a calculator handy, pause the video and get yourself a calculator. Molar mass is the mass in grams of 1 mole of any pure substance. This is the definition of molar mass. We've talked about this a little bit already, but we're going to review it. When I say no rounding, all digits are significant. You have to use what is on your periodic table. That'll give you the correct amount of digits. So when we count atoms, remember a subscript after parentheses distributes to the elements inside. So for example, Fe written as with permanganates, that's a polyatomic ion. If we actually drew out the whole thing, okay, it means that there's 1 iron bound to 3 permanganate polyatomic ions. But what does this actually mean? This actually means we have, we have 4 O's up here. So 4 plus 4 plus 4. So we have 12 oxygens and 3 manganese. Okay, so we distributed. And like I said, you can, if it helps you to draw it out and count them all, you can do that. Or you can just distribute like you would in math class, right? 3 times 4 is 12. 3 times 1 is 3. Okay, we're going to do this again. So, total number of baryons, this too does not distribute to anything outside of the parentheses. So there's still only 1 barium. The 2 will distribute to everything inside of the parentheses, but it can't escape from there. So I've got 2 nitrogens, and I have 2 times 3, 6 oxygens. That's a multiplying. So multiply. All right, we're going to keep counting. Okay, I'm going to distribute inside of the parentheses. So the 2 will go to the oxygen, the 2 will go to the hydrogen, and the 2 will go to the carbon, but not the cadmium. Okay, so we still only have 1 cadmium. Now I'm going to look. 2 times 2 is 4. So I have 4 carbons. 2 times 3 is 6 hydrogens. 2 times 2 is 4 oxygens. Okay. So, little bit of review. The mole, remember our friend the mole. The mole is just an amount, okay? The amount of particles in 1 mole. It's just like an amount, like a pair is always 2. A mole always gives you the amount of particles in a substance. So it is 6.02 times 10 to the 23rd is the amount of particles in 1 mole. Just like 1 pair is always equal to 2, 1 mole always has 6.02 times 10 to the 23rd particles. So particles can be anything. Not anything, but when I say particles, it can be either referred to as a molecule, or atoms, or protons, electrons. These are all under the broad category of particles. Okay. So if we want to determine the molar mass of compounds, we need to calculate the molar mass of each individual element, and then we can put them all together. This is important. The units are always grams per mole, or G per mol. That's our abbreviation. So, let's do some examples. Dinitrogen monoxide. This is my formula, N2O. So I have 2 nitrogens. And I'm going to multiply that by the molar mass of the nitrogen, which is 14.007. So get your calculator out and just put that into your calculator. So I'm going to say 2 times 14.007. Okay. So you're going to get 28.014. And then we're going to do the same thing. We only have 1 oxygen though, because remember, it is understood to be 1 if you don't see anything right here. So this is understood 1. That's an understood 1. Okay, so that's going to be 15.999 is your total. Because this is an understood 1. And 1 times anything is just itself. Then at the end, you're going to just add those together. So once we get these numbers, we're going to add them together to give us our total molar mass. Okay, so you're going to take it. You're going to say, okay, 2 times 14.007 is equal to 28.014. 1 times 15.999 is equal to 15.999. And then I'm going to add. You're going to add these together to get your total. So add them together. Add 28.014 plus 15.999. And that's going to give you your total of 44.013 grams per mole. Okay, let's do another example. Potassium sulfite. So this is a good problem because it's a nice review of a lot of different things. First things first, we have to write our formula, and this is an ionic compound. So that means it's a 4-step formula. 4-step formula. We got to get that formula first. So we're going to, K, that's my potassium. K, and then sulfite, ITE. Oh, that's not ide. It's not sulfur. I need to look at my polyatomic ion list. Sulfite. So that is SO3 with a -2 charge. with a -2 charge, and our potassium has a +1 charge. Oh, that's right, I got a crisscross, so that 2 is going to come over here, and the 1 is going to go over there. Okay, so I know now that I have 2 of my potassiums because of my formula that I just wrote. I have 1 sulfur, and I have 3 oxygens. Okay, so we're going to keep going with that. Next part, you want to be looking, once we have these written in, 2, 1, and 3, the next place you want to look is on your periodic table to get the molar mass. This is from the periodic table. Okay, so I have 2 times the weight of potassium. Look at your periodic table. Look at that molar mass. So that's going to be 39.098. Okay, and I'm going to do that for all of them. All right, so once we put in, again, these numbers right here are from the periodic table. Those are just the molar masses from the periodic table. Then you're going to multiply them by those subscripts. Our final step is that you have to add them all together. So to finish it off, you have to say 78.196 plus 32.066 plus 47.997. And that gives you your final answer. Okay, so we're going to get some more practice on the homework tutorial video, which will be coming up soon. Great job.